Hello and welcome to our one-day IDTX special for the end of the year. Thank you for joining us. Please do, throughout the session, be active in the chat. Let us know where you're joining from, what you're looking to get out of the session, and maybe if you've heard John speak before. Because those who don't know, John, you spoke a lot of things, John. I know that's kind of how we first met through World of Learning and the Learning Network. And always very, very informative. So I'm looking forward to this. Just need to start off by saying a massive thank you to all our speakers, everyone attending, and of course, our event sponsors, Evolve L&D, L&D Free Spirit, and Little Man Project. I'll include links in the comments for those throughout today, but I'm going to hurry up and get out of the way, hand over the reins to you, John, as everyone's here to listen to what you've got to say. Thanks ever so much, and over to you.
Thank you, Tom. I'm just looking at the chat actually. Linnea, so hyped for this session. Oh, I hope I can deliver on the hype. Yeah, so I've been talking about lots of different things across e-learning over the years. I'm an independent consultant. I'm an instructor designer. I don't sell any tools. I just sell my time. So generally, I cover a broad range of topics around learning design, tools, and platforms. So this is a recent sort of, I think we're all interested in neuroscience and what we're learning about the brain. And one of the things that I came across in the last couple of years, and I think is really interesting, is schemas and mental models. So I'm going to cover in this session. It's a brief session. I'm going to go through things quite quickly. I'm sure you'll be able to keep up. There's a few exercises for you to do. There's a couple of Slidos. So if you've got your phone handy, I'm going to share a QR code. You can join in with the Slido polls. Yeah, okay, good. Let's go. So first of all, I think a lot of people may think that the brain is a bit like a computer. Well, actually, in the research on the things I've been doing recently, it is absolutely not like a computer. It is so unlike a computer, it's hard to describe. And we'll come back to that shortly. So various people over the years have right back to the Greeks and Romans tried to work out, how the brain worked and how it was organized. Some people came up with this idea in the 18th century. It was called phrenology. Now that was actually about parts of the skull. It was parts of the skull touch certain parts of the brain, so they must be involved in certain things. Clearly, that is totally wrong. I'm sorry if there are any phrenologists out there, but sorry, there's no evidence for any of that. However, we do understand that various parts of the brain appear to be involved in doing specific functions. So there are certain areas of motor control, for taste. Now, it isn't just that area, just that those areas are primarily involved in that. In actual fact, when you do something like smell something, although one area is most busy, lots of other areas are also involved. So actually, it's much more complex than this sort of simplified diagram would let you believe. And we've learned about this mainly by people having issues, or people who've maybe got brain damage. So recently, with MRI scanning, been able to look at that subject who've got a brain injury and work out how the brain, how this is somebody moving their right hand. So at the top is somebody who doesn't have an injury, and the bottom is somebody who's got suffered from a stroke. So that has really helped us sort of map out, what bits of the brain are doing various things when we're doing things. So the brain is quite complicated. So what it's nice though, if you're a learning designer like me, and hopefully like you guys too, it's nice to have a sort of simpler model that we can use. So this is generally accepted as a simpler sort of model of the brain. So every day, masses and masses of data goes into our 5 senses. So I went for a walk this morning. I saw a yellow Mini in a drive. I thought, well, that's interesting. But most of the things I saw on my walk, just the masses and masses of visual data, the sounds, the smells, go into sensory memory and are quickly lost. Sometimes you pay attention to something like that yellow Mini, and that goes into your short-term memory. And for a short period, it stays there. So I came home and I said to my partner, oh, this house, they've got a nice bright new yellow Mini. I sort of rehearsed that in my head and told her, and she'd been for the same walk and hadn't even noticed it. So that short-term memory is also quickly lost. So although some stuff does make it into short-term memory, it's quickly lost. in order to remember things on a much more longer term basis, we need to do much stronger encoding, and that encoding process puts things into long term memory. So maybe I'm in the pub next week and we're talking about cars, and I mentioned that yellow Mini, and what I'm doing is I'm retrieving that. So that's all part of the encoding process. However, in a month or 2 months' time, I'll completely forgotten about that yellow Mini. But generally, stuff that makes it into long term memory stays there. A little bit is lost over time, especially as we age, but generally, if you can get it into long-term memory, it generally stays there. Good. Anybody recognize who this person is? I mean, you wouldn't have met them, but anybody, anyone hazard a guess as to who that person might be? I mean, if you're L&D people, you've definitely come across this curve. The curve is named after him. Ebbinghaus, well done, well done. Who was that? That was Michelle. I hope you got that right, Michelle. So basically, Ebbinghaus did a bit of research. It wasn't, properly it was research on himself. He basically set himself the task of remembering lots of these 3-letter combinations. All of them were meaningless. He specifically chose them so they'd be meaningless. And he memorized a whole load of them. And over time, he checked to see how many he could remember. And surprise, surprise, as time went on, he forgot more and more. And that is now called the forgetting curve. And it's pretty clear that if you don't actually retrieve or do something with it, it is basically lost. And the reason that is, encoding is effortful. So putting stuff into long-term memory is really, really hard. As a learning designer, that's something that we have to grapple with every day. You get the sensory input, the short-term memory, but putting stuff into long-term memory is really, really challenging. Okay, the brain is capable of remembering lots of stuff, but in its normal steady state, it doesn't really want to, which is why taking your kids to school, get them to learn stuff is quite hard. So I've got a very simple question here. So I want you to grab your, very shortly there, I want you to grab your phone, scan that QR code, or go to slido.com and put in that number, slido.com 3121497. And I want you to let me what you think. How much data does our brain store over a lifetime? So that's over our entire lifetimes. How much information in computer terms does it store? Is it 128 megabytes, 256 gigabytes, or 2 terabytes? I'll leave that there for a short while. We've got 6 voted. And numbers are rocking up. Okay, so the most popular answer is 2 terabytes, followed by, coming up close second, 256 gigabyte. Okay, well, I think I will declare the winner here, 2 terabytes. In practice, unbelievably, our brain, they believe that it stores only 128 megabytes of data over our entire lifetime, which is 2,484 pages of text. That's quite a shocking fact. Now, you can read the source. There's lots of sources for this, but basically, we actually store in computer terms a very, very small amount of data in our brain. That's not the way our brain works. Our brain is not like a computer. Okay, so I'm going to do a little exercise now. I'm going to show you a map. The map, I've highlighted 6 cities in 6 different countries. I'm going to give you 30 seconds to try and encode them. Okay, so and that I don't want you to write them down. I just want you to try and remember them. Okay, so ready? So 30 seconds from now. 6 cities: Graz, Bari, Timisoara, Plovdiv, Kherson, and Konya. 12 seconds gone. 15 seconds, you're halfway through. I'm not trying to press you or anything. "30 seconds. Good. We'll come back to that later. Okay, so if you are having to learn something, say, I don't know, you're going to do an interview or you're going to study for an exam or something, if you want to effortfully try and remember something, some fact or something, how do you, what encoding techniques do you use? So once again, use if you're on Slido, it's the same link. So you can choose as many of these answers as you want. So what you do in order to help your encoding, in other words, what you do to help move information from short-term to long-term memory. Make notes, good. Practice it, excellent. Read and highlight my notes. Oh, not many drawing a picture. Oh, there's a few drawing a picture. Talk to someone else. Yeah, good, good. Quiz myself. Space repetition down there. Make notes seems the biggest. Practice it. Good, yeah. I mean, I find making notes really helpful. I like it when I'm doing a presentation and people are actually making notes, even though I normally give the slides afterwards, because making notes runs things through your own sort of brain, and you're not writing down what people are saying. You're actually sort of writing down your interpretation of it. Brilliant, good. Okay, all of those things are actually quite helpful. So what do we know about long-term memory? Well, there's a few things we know about long-term memory. First of all, there's two key parts to it. There's what we call semantic memory. That's facts, concepts, ideas. I'm going to ask you about those cities and those countries. That comes into that. And then we have what we call episodic memory. So when I went for my walk, I experienced the environment, and that is like when you go on holiday, you have memories of your holiday. That's not really stored in semantic memory. That's stored in episodic memory. And in practice, we know that actually episodic, those aren't actually stored, and that's why we store so little. Those are recreated from little tiny bits of data. So we went on a holiday to Cyprus, and we create memories of that from the little bit of data we actually store. And we also have what we call procedural memory. That's the sort of things you learn to do, like riding a bike or brushing your teeth. So they're to do with motor and cognitive skills together. It's very hard to you have to just practice those things in order to learn them. So I'm going to talk about then schemas. So that's primarily related to semantic memory, as you probably imagine. But also we're going to talk about mental models, which sort of take all of those things together, semantic, episodic, and procedural memory, and enable us to do things, which is actually what most of us are learning. And certainly in the workplace, we're learning in order to be able to do something. So schemas are very useful, but we also need to apply a mental model. So what is a schema? You may have come across before. It's used quite a lot in psychology. I'm not a psychologist, but it's a term that's used quite a lot in psychology, and it's been used, over time in education as well. So they're like categories. They're sort of like a simple blueprint of how we come to understand bits of the world. So and let's think about what that means. So if I asked you to draw a house, most people's view of a house would be something like this. It has some walls, some windows, a roof, and ideally a door. This one's got a chimney and a bit of a garden. It doesn't need that, but that's a very simple schema of a house. But if I asked an architect about what their schema was, that would be much more complicated. So, and that's what a schema is. So we have simple schema for things we're just learning, or maybe we're not really interested in, and we have very complex schema in the areas that we are interested in, or we are experts in. So, and as we learn, our schema become more and more complex. We add more bits on. We identify other schemas. We try and join schemas up. So actually, it's a really important concept for actually building knowledge and understanding of the world. I like to sometimes liken it to a jigsaw puzzle. We're building this massive jigsaw puzzle in our head, and we're joining pieces on, or we can't join a piece, or we join some pieces together, and then later on we can join that group to another group. So we're constantly moving around, constantly moving these pieces around in our brains in order to create our schema of the world. So another little exercise. So this time I want you to actually use one of your schema. So I'm sure you've all got some sort of bike schema. When I say a bike, I don't mean a motorbike, I mean a pedal cycle. So I want you to draw a bike from memory, okay, and make it exactly as you can, and include all the key working parts. So the main working parts, so it has pedals maybe, and some way of turning the pedals, handlebars, whatever. So I want you to got 2 minutes to do that. Draw a bike. Just grab a piece of paper and draw a bike. And then when you're done, take a picture of it and upload it to Padlet. So if you just scan that, that QR code, that'll take you straight to Padlet, and then you can just upload your picture to Padlet. Good. You've got 2 minutes. Off you go. Normally I'd walk around the room and see how people are getting on. Sadly, I can't do that. Good. I've had a couple up. Sadly, we're both called Sneaky Eel. But when you upload it, put your name in if you want, or something else in. Tom, age 33. Oh, I quite like that, Tom. It's very, very high speed drawing, but looks good. Good. Okay, we're going to leave. We're going to come back to that bit later on. It's surprising, actually, how it's surprising, actually, when you do this exercise. Oh, that one, Joe, very nice. Very nice. Well, shadows at the end, okay? It's surprising, actually, when you think you understand what a bike is. When you try and draw one, I mean, apart from the fact, obviously, people don't always necessarily they have the drawing skills. Remembering exactly what a bike looks like is quite hard. So this exercise was done. But a lot of neuroscientists use this exercise. So this is Carla. So you can see that they've got pedals, but they're not connected to the wheel. Jane, age 7, has got this massive great chain thing, but and then this is Serena, and then this is Mark. And so Mark's probably got it most accurately. So actually, it's surprising when you think about this, how we don't really, how our schema aren't as good as we think they are. So I'm a road biker. I've got this book, Bike Maintenance. Leonard Zinn's schema is I take my bike to a repair shop, and my God, there are so many bits. It's much more complicated than even I understand. And we have conceptual schema too. So obviously those are bike is a physical object. It's sort of a bit easier to think about a schema there. But we have conceptual schema. So we have like a project schema. We even have a schema for our friends, or going to the pub. We might have a going to the pub schema. So we have an organism. We have things we expect when we go to the pub. So those are all schemas. You can have schemas for lots and lots of different things, physical and sort of conceptual as well. One other study that was done to sort of counter Ebbinghaus, because Ebbinghaus tried to remember meaningless stuff. So another guy called Frederick Bartlett said, well, actually, that's not realistic. When we come to try and remember stuff, we already know stuff. So what we try and do is we try and connect that, what we already know, what we call prior knowledge. So he did an experiment called the War of the Ghosts. he had a whole host of university students. He told them a story. It was a Native American story called The War of the Ghosts. And then a week later, he asked them to repeat the story. A month later, even years later, he asked them to repeat the story. And surprise, surprise, over time, they completely changed the nature and the meaning of the story in order to fit with their own schema, their own conceptual schema of the world. A bit like a sort of complicated Chinese whispers experiment. So in practice, the way we remember things depends on what we already know. And that's a really important, I think, a really important fact if you're going to be involved in learning design. Good. Okay, so that's a schema. What's a mental model? Well, a mental model sort of takes things a step further and enables us to act, enables us to do something. So it sort of approximates the real world. A model is something we try out. It sort of approximates reality. It sort of works, and we try it again. So a mental model is a way of doing things in the real world. So here's our car schema. So we have a schema of a car. If you drive a car, it's probably reasonably good. So then we have driving a car mental model. So we have a car schema and we have a mental model of driving a car. So for example, we get in the car, there should be a steering wheel, there may be a gear lever or not, and there's brakes, all those things. If none of the things are not there, like with an automatic car, or my partner recently had a car that's got no handbrake, it's all automatic. Suddenly your mental model is thrown a bit into confusion, but you adapt it. You sort of adapt your mental model to cope with the new situation, as long as nothing too much has changed. But fixing a car is a completely different mental model. They both rely on the car schema. Obviously, for fixing a car, the schema is much more complicated. But both those mental models are very, very, very different. I'm sure lots of you have a good driving the car mental model. Some of you less good fixing a car mental model. And you can tell if you're with somebody who's good with cars and you're driving along and you hear a strange sound, and you've got a driving a car mental model. It's, well, what's that strange sound? Whereas somebody who's got a really good fixing the car mental model goes, oh, it sounds like the alternator belt or something. They have a sort of a model of what that might be. It might be wrong, but it's something that gives them a clue as to how they might go about either fixing it or getting help from outside. So you all have a bike schema. Here's a really nicely drawn bike. I didn't draw that. It's a very accurate drawing of a bike. So will you, if you have a good schema of a bike, will it help you fix a tire? Well, a little bit maybe, but there's lots and lots of things involved in fixing a flat tire. Something pretty simple that you've got to learn. You've got to test out. So your schema will fail until you actually sort of practice some of this stuff. So actually doing some of that is actually much harder than you would otherwise imagine. So yes, the schemas basically are sort of map of the sort of our understanding of the world, a bit like opening up a map. But then if you want to get from A to B, you need to be able to navigate using the map. And a mental model sort of gives you that. It basically converts your sort of schema into the ability to take action. So if we're teaching people stuff, we need to give them the basic schema, but we also need to give them enough of a mental model to actually do something for at least the first time, so that they can start to learn it. And experts rely on very strong mental models. So what makes all of you here good at what you do is strong schema and then really strong mental models. So maybe you've developed a project plan 100 times. So you've now got a very, very strong mental model for project planning, and that's yours. It's uniquely yours because you are unique. The way your brain has learned things is unique. So it's different to another project manager's mental model, and that's what makes us unique as humans. And we need to celebrate that, because AI is, I'm sure you've all been using AI. It's very strong on schemas and its knowledge, but it's less good at actually doing stuff. Ultimately it's going to get better, I'm sure, but AI is very good with the schemas and supporting people, but it doesn't have the mental model that experts have, at least not yet. So one of the things that really really makes your mental model powerful is practice, and what we call deliberate practice. So practicing specific parts. For example, if you're a sports person, you practice every day, even though you're really good. You practice every day. If you're Lando Norris and in F1, every day he's practicing, making himself better. So what they call deliberate practice, working on specific things, and all that basically builds a much stronger mental model. So there was this thing of 10,000 hours. So we need 10,000 hours to become an expert in something. So how does all this understanding about schemas and mental model, which is pretty conceptual, how does that help us, as learning designers, as instructor designers? How does that help us to teach people better? Well, first of all, we can help create new schemas. So we can help build new schemas. People are and something they're brand new to. We can build upon existing schemas. One of the things we would like to do as learners is, well, what they already know. What is their bicycle schema like? Is it broken in some way? So we can fix a poor schema. So often, when I come to teach people stuff, it's often to do with that they have a misunderstanding around something. So if we can fix that, that goes a long way to improve learning. And also we can connect schemas together. So maybe we can connect our motorbike, a car, our bicycle schema to our motorbike schema, and sort of join those things up and use things like analogies. That can be really helpful, helping people learn. So that's schemas. What can we do with mental models? Well, first of all, we can show a simple, concrete example. So start with something simple. So in the flat tire example, maybe what we could do is take the wheel off the bike and then just start with the wheel off the bike. So we start with a simple example, and then we can move up to more complicated examples. We can explore analogies, so we can sort of compare with something that they already know. I remember when I was learning electronics at school, they compared it to water flowing in pipes and tubes and things, and I found that really it explained how a resistor or a capacitor worked, and I found that sort of analogy really helpful. We can explore different real world situations, so trying things out in different situations is really helpful for mental models. And then we can start to explore slightly more complex cases, and then we can also use decision aids developed by experts. So experts say, well, look, here's a checklist, try this. Those are very helpful. And finally, deliberate practice. So I think, as most of you said earlier on, practice makes perfect. And things like, people sort of, Kolb's learning cycle or Bloom's taxonomy, that's not, or even things like learning styles. They say that's not the way the brain works. That's not how the world works. Well, of course it isn't. So Kolb's learning cycle isn't meant to be an accurate representation of how you actually learn something. It's meant as a model or a scaffold to help you design learning, to think about learning. It's a thinking tool. All these models or scaffolds are thinking tools. Learning styles, Bloom's, they're all tools to help develop a mental model that you can use in the real world. And when I'm designing learning, I use this very simple thing. I mean, it's crazily simple. The absorb, do, connect is in a book called E-Learning by Design by William Horton years ago. And this absorb, do, connect, it's a very simple model for designing learning. And even though I'm a very experienced learning designer, I still find this useful to get me back on the right track. And also it's really helpful when you're teaching people how to do instructional design or to do learning design. Good. Okay, so we're just about at the end. So now I'm going to test out your encoding skills. So can you remember the countries in which the 6 cities were located? So yeah, so please, so type into the chat as many of those as answers as you know. So Barry, where's Barry? That's the easy one. Yeah, type into the chat if you can. Barry Island. No, Barry, B-A-R-I, Joe. Bulgaria, Italy, Turkey. Wow, how can I not recall these? Good. Okay, I'll just I'll relieve you of the yeah. So basically, yeah. So Bari is in Italy, Graz is Austria, Timisoara is in Romania, Plovdiv is in Bulgaria, Konya is in Turkey, and Kherson. Why would probably most of you got Kherson? Why do you think most of you shouldn't have got? No, Moldova is a country actually. Why wouldn't most of you? Oh, okay. Yeah, so probably most of you got Kherson because it's in Ukraine. It's been in the news recently. So anything that connects to what you already know. Yeah, sorry, you're right. There was no country listed, but yeah, you're right. Sorry, sorry, Michelle. There's no country listed. Yeah, but yeah, I didn't. Maybe I'd assumed too much prior knowledge in that one. Good, brilliant. Thank you. So yeah, I really like this. I really like this quote. Yeah, we're given, our brains are capable of enormous capabilities, but actually we don't use that nearly effectively enough. There was another quote I had from Homer Simpson, who says, whenever we learn something new, he has to push something out. Whenever we learn something new, he has to push something old out of his brain. Our brains actually don't work like that. So a book I recommend, definitely recommend, I really recommend anybody who's involved in learning design to read The Forgetting Machine by Rodrigo Quiroga. Just a brilliant book, not too long, really well. He's a cognitive neuroscientist. Yeah, he made the Jennifer Aniston neuron famous. You can read about it in the book. Yeah, I've done a blog post on it, so I can share that. I'll share that later. And then these are another two books I really like. You know, Why Students Don't Like School, both written by, well, Daniel William is a cognitive neuroscientist, so a lot of stuff around cognitive neuroscience and about learning. Another great book too about how we learn by Benedict Carey. And then if you've ever been to the Learning Scientists website, really good stuff. Really good stuff about cognitive neuroscience and learning. Brilliant, good. That's it. I think I'm a minute over. I'll just kind of stop sharing this now. If you want to copy the slides, yeah, do drop me. Yeah, just drop me a message on LinkedIn or on X. I know people are going off X these days. Yeah, drop me a message on LinkedIn and I'll send you a copy of the slides. Or maybe Tom, I can upload a copy of the slides to the IDX website at some point.
Yeah, absolutely. We can wherever they're stored, we'll make sure there's a link to them as soon as possible in the comments in the description of this video. Thank you so much, Jonathan. I think there was loads in there for us all to unpack. If anyone has got any questions, do chuck them in, and we can always kind of come back to them in the future. Other than that, though, I'd like to say thank you so much for taking the time out of your day to join us. First thing in the morning, no less. Well, first thing in my morning. You can kind of guess what sort of time I like to get up from that comment, I guess. And John, thank you so much for coming and sharing your insight with us as well. Our next session starts at 11 with Jason, so hopefully we will see you all then. And again, just another quick thank you to our sponsors, Evolve L&D, L&D Free Spirits, and Little Man Project. Thank you all so much for your time, and we shall see you again in the next session.
Thank you all. Thank you. Have a good day, everybody.